Okay. Thank you very much for giving me this opportunity to share some of the works we have done here with all of you. And I hope this will help somebody. So this topic is, maybe I'll turn off my video so that
Sure.
bandwidth. The topic is audio tokenization for efficient audio retrieval. I'll explain these terms as we go. So let's start with something very simple, speech.
I am running.
So the simple sentence which says,
I am running.
I am running. And it has an acoustic form. We hear it and we understand it. We can record it with our microphone and it can be played back. But then we can do something more interesting with it. Let's say we can tokenize it. We can say what I am hearing that can be written in a visual form, and I can understand that in my speech there are phonemes or phones. So what are phones? Basically, it will say there is a sound called ah, and this sound is again there, but maybe in some different realization. And then I go to phonology, which says that this ah and this are actually same phoneme. So they're different phones. They could be different phones, but same phonemes. So in this way, we see that how the acoustic form is kind of understood, or we find the relationships between different sounds, and we can write them in this way. And then we go to another level where we come to a level of orthography, where we make spellings and we use it for textual communication. Now, coming from acoustic form to orthography, it gives us various advantages. We are able to study the relationships between different sounds, how the sounds change when we change the context, etc. And then we use it for communication. And one very good advantage is that the whole thing is very compressed. It's very compressed form of representing the message or the acoustic form. And then from orthography, we can do further analysis like morphology. We can go to syntax. Syntax means like verb comes, and then nouns are there, then objects are there, etc. And then we go to semantics, and then we can go to pragmatics, and ultimately we get the clear picture that, okay, this is what it means when I say I am running. There is a complete understanding of the context around. So this is what we do in linguistics. I will focus in this talk on orthography, because the reason is that orthography is a very compressed representation of what I want to speak, or what is the acoustic form. Acoustic form, it's long, many samples if I want to save on computer, but orthography is a very compressed form. I can do very efficiently. I can search, I can understand. So let's focus on orthography. It's the written form. It's a very compact representation, and it distinguishes sounds as meaning carriers. And it can be used for further analysis, etc. Now, the question is, do we always need some humans to make the orthography? Can we automatically derive orthography using some machine learning or some other algorithms? Can we make a sound to orthography converter? Somebody can say, oh, we already have ASR. Using ASR, we can directly get the textual form from the sound. But ASR is for languages that already have one orthography. Let's say I do ASR for English. I train my model saying that, okay, this is my audio and this is the corresponding textual representation or the orthography. And the model learns this mapping from audio to text. So this ASR is for languages that already have an orthography. But many languages, they don't have an orthography. We have, even in India, we have so many languages which don't have an orthography. If we go to Himalayan regions like in Himachal Pradesh or that northeast side, many languages don't have an orthography. And further, there are so many dialects. There could be many dialects of a language, and we don't have orthography for every dialect. What about music? Music has no orthography. Means, okay, music can have some written form, and especially for Indian classical music, which is very rich, there are still debates about orthography is, can we stick to one representation? Because music is so rich, can orthography capture all of that? Sorry. What about bird sounds? We know birds communicate. Birds have there are very strong evidences that birds communicate. But do we have understanding of their sounds? We can record all the audio data, but do we understand their language, or do we understand the can we make an orthography relationship between sounds? And practically speaking, these are all scientific topics, but for technology, from technology perspective, it has a very good utility. We can use it for audio search.
I think somebody has their mic on. Can everyone turn off their mic, please?
Okay, I'll do that. Okay, thank you. So let's come to this. I will focus in this talk on this last part, the technology part, that we are making an orthography for audio search. We are not studying the scientific problems yet. So what is audio search? Audio search means we have a large database of many audio files. And I have, let's say, a query, or which means I have a small snippet and I want to find where is similar audio in the entire thing. Imagine you have NPTEL videos or some lecture videos of maybe 20 hours or 50 hours or maybe thousands of hours. And I want to search a particular term. I can speak it, I can record it, and then I have to search it in the huge database. Or maybe it could be simply a snippet which I got from YouTube, and I want to find in the original database, where is it lying? For example, we are working with Doordarshan or All India Radio. They have lots of data, and I just used a small snippet and recorded it on my phone. Let's say it was playing in the television or radio. I recorded it, and now I want to find out what is the original audio and where is the original audio. So all these things are relevant problems. Now, one very good approach or efficient approach to do this is convert the audio into some kind of compressed representation, could be a sequence of vectors, and do that for every audio in the database, and do the same thing for the query audio. And then in this compressed vector representations, I can do the search. I can search, I can have a matching algorithm, which will efficiently match this representation with all these representations and find out the best match. And finally, I will get, oh, this was the original audio. So this is the problem of audio retrieval or audio search. Now, it has two components, which are kind of research areas. One is, how do we learn these representations so that my search is effective and also very efficient? The second thing is the matching algorithm itself. What algorithm should I use for efficient retrieval? Now, there are some good works already existing in the literature, like we know about Shazam. Shazam is, so what Shazam does is, it gets these representations from the spectrograms. We have a spectrogram, it has peaks, like high energy points in the time frequency representation. And these peaks are, first of all, identified, and then we find some kind of relationships between neighboring peaks. And this relationship is then encoded in the form of a vector representation. So this is the representation. Now, for efficient search, something called hash tables are used. So that vector representation is via a hash hashing algorithm. It is converted into some hashes, and then those hashes are searched. Whenever I have a query audio, that from that I extract these hashes, and then original audio has hashes, and we search and retrieve the audio. That's how Shazam works, and it's a very old work. It's all rule-based. This is not machine learning based. And then we can have more recent algorithms, which are learning-based algorithms. And there are several of them. One is, one kind of approach is based on audio segmentation. So what we do is, we have long audio. We segment it into small segments automatically. So for example, we may map every frame. Let's say, we have a long audio, we extract small frames at periodic intervals or at uniform intervals, the simple frames, and each frame is mapped to a vector using some form of self-supervised learning or some, maybe even ASR model we can use if we have one. And then we can cluster these frames to make these segments. So based on clustering, I can make these segments. And then for every segment, I can assign a label, or maybe these cluster centroids can be used to discretize the whole thing. And then I can do the search over these segments. Another approach could be, I don't use segmentation, but I just have these feature extractor. These are learned in a self-supervised way, like we all we are very familiar with Wav2Tok methods. Wav2Tok approach is very popular approach. I will discuss it in little more detail in the coming slides. And then we search over these representations. So, and then comes the matching algorithm. For matching, so one thing to note is that this is sequence matching. This is not vector to vector matching. Well, if we have simply two vectors, we can just take their dot product, or we can take their Euclidean distance. That's a good enough way to match vectors. But these are sequences. So for sequences, we use either dynamic time warping. If these are sequences of vectors, we can kind of create a similarity matrix or adjacency matrix, and then search over the best path in that matrix to find the alignments. For example, these two are there, and I know that this trough and this trough, they match. So this is the dynamic time warping algorithm. And then we could have edit distance if our inputs are discrete. Like this is a continuous signal. If it is a discrete signal, then I could use edit distance. Discrete means I have a sequence of discrete tokens, then I can use edit distance. Okay, so what is dynamic time warping? You have two time series, and the cost is defined for point-wise difference. Let's say I know if x1 one entry minus another entry, this distance I know, but I want to find the distance in the sequences. Then I have to find the best path, and then we use Bellman's optimality principle to find this best path. Okay, so this is the preliminary understanding we have for audio search. I will little bit recap on Wav2Tok kind of approaches to learn audio representations. Audio representations mean what? I can say my audio is a time series xt, where t goes from 1 to capital T, and I want to map this to a sequence of vectors. So zt, so every zt is a vector, and t goes from 1 to t tilde. T tilde is generally less than or equal to capital T. So my xt is a sequence, and then my zt is a vector. So this is how it looks like. I'm mapping my input sequence to a sequence of vectors. The other approach is that I map my input to a sequence of discrete representations or tokens. So every YT is a symbol from an alphabet. A is an alphabet, which means it's like a set of discrete tokens, and YT is one of those tokens from that. So let's say this is my YT. This looks like discrete tokens like W, V, B, L. These are all discrete symbols. Okay. We know ASR does it. So how ASR does it? ASR maps my speech or the continuous signal to a sequence of tokens. Let's say this is a sentence. This is the acoustic form of 1, and my final orthography is ONE1. That's a sequence of tokens. And how do I do this mapping? So first of all, I extract the time frames in a uniform way, and then I map them to some acoustic parameters. This could be a rule-based approach, means the MFCC features or STFT features, etc. And then I have a acoustic model. This acoustic model could be a Gaussian mixture model or a neural network, which extracts the probabilities of phonemes or senones. Senones means like subphonemic states. So, and then I use something called hidden Markov model to construct a path or to basically link those synonyms to form phonemes. And then I use some kind of grammar model or language model to, to sew them together, to thread them together to make a sentence or a word. Like this v, a, and na, these three different sounds, the different phonemes, they make the word one. And then I could have linguistic language model at the sentence level, where I can make the grammars, let's say 1 followed by 2. Let's say I say, I am going to, etc. So all these syntactic rules can be captured by a sentence level model. Okay, now this is a supervised approach to learn the tokens, where we have the audio form and the tokens available for training. That's what we do in ASR. But let's say if we don't have the supervised form or the orthography available, can we learn it in an unsupervised or self-supervised way? So one way, okay, so the idea comes from NLP. So in NLP, a very simple representation, we have sentences. For example, we can get like gigabytes or terabytes of sentences from internet, from Wikipedia, etc. They have very good sentences available. So how do we do learning? So let's say we have a word W0. I will look at a few words before this and a few words after this. Now, using this context, the previous words and the following words, I want to predict the center word. Let's say I'm saying, let's say if I say, I am visiting Bombay tomorrow. So this is a sentence. Now, if I take visiting as the word, the first two words are I am, and then following two words are visiting Bombay. No, sorry, visiting is the word, and Bombay tomorrow. And I'm looking at I am dash Bombay tomorrow. I want to predict the word visiting. So this is a kind of self-supervised learning. And this model tries to predict the word visiting, looking at the context words. This is called the SIBO model. This was pioneered in NLP, but then people are using it for audio as well. So in audio, what we do, we have a long audio, and we make small windows out of it. First window, second window, third, fourth, five windows. And now I am mapping these windows to some vector representations called C, or context representations. Oh, sorry, some vector representations. Now I am able to see these 4 windows, first 2 windows and the last 2 windows. And I want to predict the middle window. I have masked it out. I have kind of hidden it from the model, and the model has to predict the representation for this window. It's self-supervised learning, idea taken from NLP, but applied to audio, and it works very well. And there are some other parts, like we also, from this kind of representation, we learn some quantized representation, Q, and then we do some other things on this part, so that we can get tokens also, or we can get some discrete representations of audio as well. So this is the process. We first mask a center frame, then we look at the context and try to predict the center word or the masked frame, sorry. And we use losses like contrastive loss, and all this is very standard stuff. So what is the meaning of contrastive loss? We try to minimize the distance between the prediction, this prediction and the actual word. And we want to maximize the distance between the prediction and the other words, which are not the right prediction. So this is what we do in the contrastive loss term. And then since we are doing some kind of mapping to discrete tokens, so for that we can use a codebook vector. Codebook, what is codebook? Basically, if I speak in simple terms, it's like you have k-means clustering, right? You can create, let's say, 5 clusters from your data. Then all those clusters will have a centroid. So let us call that centroid as the codebook vector. And then all those vectors which are mapping to the centroid, they can be assigned that codebook vector. So let's say we have 5 clusters, then this means we have 5 discrete representations, or basically 5 representations. So in this way, we can discretize our data. That's what the approach we use here. And so but the problem here is that all these representations could collapse to a single output. Now see, even the space is learned and the clusters are also learned. It is very much possible while learning, our whole space may collapse to one cluster. So to avoid that, we add another term, a regularization term in the loss function, which is called entropy. We try to maximize the entropy also during our training. So what is this entropy? Simply P log P. So probability of codebook vector that we want to maximize this entropy so that we ensure that everything does not collapse to a single codebook vector. Yeah. So basically, let's zoom out a bit. So what we are seeing here, there are two main concepts which we see here. One is we want to map our continuous representations to some kind of codebook vectors or discrete representations. The second thing is we want to avoid the case when everything collapses to a single output, which means we want to maintain the distinction between audios, right? That don't represent everything with only one alphabet, but let's have distinction so that every word or every utterance I have, it has a distinct representation. Okay, so with this background, now we are ready to understand, I'm ready to present our method, which we have proposed. So let's say we have two sounds.
Govinda. Govinda.
So both these audios, they are having the same linguistic content, like the word is same, which is spoken here, but the way it is uttered is so different. It could be different speakers, could be different emotion with which it is spoken, could be different context, could be different quality of sound, etc., etc. The goal is we want to map both these audios to the same set of tokens. In English, I will map it to GOVINDA, right? But now I want to learn it in an unsupervised way. So the problem is formulated in this way. We have a pair of audio, like this one and this one. And I want to find a map F such that this map basically maps them to a sequence of tokens or a sequence of vectors such that the edit distance between those tokens is minimum. So now this looks like a difficult problem. Why? Because in ASR we do that, but in ASR we know the targets for training. Here we don't know the targets. We only know that these should map to same set of tokens, sequence of tokens. But what are those sequences of tokens? I don't know. So that's the challenge. So directions are okay. We can use some ideas from ASR that ASR does it with the help of connectionist temporal classification, which is an end-to-end variant of hidden Markov models. Hidden Markov models use Gaussian mixture model, and then they use FSTs, but CTC does not use any of them. It has a single network which directly maps the audio to some tokens. And yeah, but we know the limitation that ASR is supervised, but we don't have any supervision available. We have no targets, but we have a pair of similar audio. So now the question comes, okay, this is slight detour. What do you mean by similarity? In music, one could have same lyrics, but different melodies. Like I can sing the same lyrics in different melodies. Or I could have same melody, but different lyrics. I could have different songs which have different lyrics, but I can sing them in same melody, right? So what do we mean by similar? Can we control this similarity? Can we control it? So this method, Wav2Tok, can control it. That's the goal of this problem, this solution. So what is the, okay, now what is the model? So X here is my input audio, and T are the tokens, and the Z are the continuous vector representations. So I map my X to some Z, and from here I tokenize them to tau. And this tokenization is done by the same codebook kind of approach where we take the dot product with the centroid, and based on that we decide our cluster, cluster ID or the token. And the terms are explained here. I will just skip this. Okay, maybe I'll explain. So this X is our input feature. It could be STFT or MFCC features. One can work with directly raw audio also, no problem. We worked with STFT or MFCCs. F is a bi-LSTM model, could be any model which has a big context, could be CNNs also, no problem. Z is a sequence of L2 normalized embeddings, the vectors, the sequence of vectors which are L2 normalized. And G is the basically inner product or the dot product with the centroid, and from where we decide the tokens. Now there is another intermediate thing here. We have this mapping to centroids, it gives us a sequence of discrete tokens L, but then we apply a token compressor. So what does it do? It just deduplicates them. Let's say if I say Govinda, then I will have G, 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 O, 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 V, 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 I, I, N. So there are repetitions. So I will just compress them so that I only get G, O, V, I, N, D, A. Right? Because every frame multiple frames will map to G, multiple frames will map to O, multiple frames will map to V. So this compressor simply compresses them. This is not a new thing. It is already done in CTC kind of training for ASR. So we used it simply to get compressed representations. So this is the architecture. Now the question is, how do we train it? How do I train it? So that training is now, so it has several parts. One part is, yes, I have two audios, X and X prime, and they should map to same sequence of tokens, like tau and tau prime should be same. That's the goal. Now, how do I go about it? So first we initialize the encoder and get some encoded representation Z, be random in the beginning, or I could initialize it with a pre-trained model, maybe Wav2Tok or something. But we started with random. So, and then we have, we initialize the codebook also using k-means clustering. We got these random vectors, which we applied k-means clustering, and we got some codebook vectors E. Sorry. And then we map our Z to E using contrastive learning. Now, this is the first term of the loss function. I want to map my Z to E, which means I want to make these clusters very sharp. In the beginning, the clusters are very diffused. I want to make them very sharp. So this is one of the terms in the training objective that I want to minimize the distance of the points within that cluster to the centroid. So this is the term we get here. EK is the centroid or the codebook vector. P tau is the probability distribution, which we get here, and we minimize it. W is some vector, some matrix, trainable matrix, basically. So this is the loss function. This is how it looks like. Simply contrastive kind of loss function, contrastive learning. Now, this is one part. I'm making my clusters sharp, but am I minimizing the edit distance between the two? Let's see that. No, certainly that is not happening. How can I do that? So, yeah, multiple L can map to a tau, that's fine. Now, this is the other loss function I'm using, CTC loss function. So the CTC loss function is already there in the ASR literature. So what it does is it will map my X to some L, the discrete representations. And I want to make sure, okay, that my X maps to some tau dash. I'm mapping my X to tau dash and X dash to tau, right? So we use each other for guiding for supervising the training. So let's say I map my X to tau dash and X dash to tau, and then I can apply same CTC kind of loss function. It's a supervised loss function. So the loss function becomes like alpha times, let's say half times CTC loss between X and tau dash and X dash and tau. And this is minimized using forward-backward algorithm. This is a standard approach to minimize in the CTC context. This forward-backward algorithm is the same which we use for HMMs also, hidden Markov models, the Baum-Welch kind of algorithm. Okay, so ultimately we get, this is our loss term, CTC loss for the cross mapping, and this loss term to make our clusters very sharp. And this is minimized using Adam optimizer. Okay, now how do we avoid the problem of collapse? Everything can collapse to a single cluster. So to avoid that, we are using an approach like EM algorithm. So what happens in expectation maximization algorithm? We first learn the centroids, and then do the mapping of the points to the centroid. So it happens in a step-by-step, or what do you say, one-by-one fashion. Like first you minimize one term, then you minimize the other term. So same approach we used here to avoid collapse. We first trained this loss function for some iterations, and then we reclustered the data because the Z space has updated because the model has been retrained. So we again use k-means clustering to get a new set of clusters, and then we resumed with our training, the neural network training. In this way, we keep going back and forth between the two steps, and we get good clusters without any collapse. So first is hypothesize the tokens using clustering, then map the audio to tokens using CTC cross mapping, then again sharpen the clusters using contrastive learning, and then repeat the whole step. Then again do reclustering, k-means clustering, and then again do this mapping. In this way, we avoid the collapse and learn the final representations. Now, okay, this was the algorithm. Now, what are the uses of this algorithm? Okay, let's assume that this algorithm gives us a model which can convert our audio form to some kind of token sequences or orthography. This is useful for spoken term detection. This is useful for query by humming. And in general, it could be one-stop solution for all audio search problems. Could be in music domain, could be in spoken speech domain, could be in environmental sounds domain, like bird sounds domain, or it could also work in other kind of signals which are non-audio signals, like I don't know, maybe we have not tested it, but we can just hypothesize that it will work, for example, for EEG signals or things like that. But the only limitation is that the information should be ordered, which means ordered means the order of inputs should be same as order of outputs. Like when I speak something and when I write something, the order is same. But we cannot use it for translation, because when we translate to another language, then the order is jumbled. In Hindi, I may say, "Main ja raha hoon," but in English, it becomes "I am going." So the am part comes later, raha hoon. So the order is shuffled. But here in orthography creation, order should remain same. If I say "Main ja raha hoon," then the written form also first has "main," then "ja," then "raha," then "hoon." Now, okay, somebody may ask the question, reviewers also ask the question, that you will need lots of data to train this model, and getting the pair-wise information is not easy. Getting the pairs of similar audio is not easy. We have to create the database. It's difficult. So we tested with unsupervised training, which means we took the only single audio and we applied some augmentations on top of it to make the other pair, the other tuple of the pair. So how did we do it? We tried methods like time stretching and pitch shifting. Because I can speak the same word at a higher pitch or at a lower pitch. So pitch shift does not change the audio which I'm considering. And time stretching, I can speak slowly or I can speak quickly. So that also does not change the semantics of the audio. Likewise, in music also, I can do the pitch shift, which means the whole thing, the tonic gets shifted. That does not change the melody. And similarly, time stretching, I can sing the whole thing very slowly. It does not change the melody. So these are the augmentations which can be used to create the pairs from just unsupervised data. This was the paper from ICLR this year. So here the experiments we did were with timid database and Libri speech database. And the metric which we used for evaluation was mean reciprocal rank score, which basically says, let's say I have a query and the retrieved list, the right hit is at position 5th position, then the reciprocal rank will be 1/5. So which means if I'm close to the first position, I will get rank of 1. And as I go farther from the top position, my rank keeps decreasing in a 1/n fashion. So ideally, my MRR should be close to 1 or 100%. So these are the results for spoken term detection problem. I represented my speech with these tokens and then did a search with these tokens. So these are the results. The MRR score is, let's say here we have 0.64, 0.74, whereas we tried, now the baselines were also not available readily. So we used Wav2Tok as one of our baselines, but we had to modify it for this problem. So we extracted the vector representations or the token representation from Wav2Tok and then used it for search. And then one simple baseline could be simply using MFCC features or logmel features and applying DDW on top of them. So here you are seeing two kinds of approaches. One is with edit distance, one is with DDW. So edit distance is very fast, but the one with the DDW is a bit slower, but it has more accuracy sometimes. So these were the results. We found improvements in terms of accuracy or in MRR, and we also found improvements in search time. And then we tested it on query by humming kind of problem. So this was ISMIR QBSH dataset was used. It was trained on 40 different songs and tested on 8 separate songs. Again, MRR was reported and with different methods. So there are, these are some recent methods, like MIPS is a recent method used for query by humming, triplet loss function, another method for query by humming. And compared to these, our method was a little better. The Wav2Tok method was a little better. But the best advantage is that it is very fast. It was very fast to search. Yeah. And we also tested with some ablation studies and we found, okay, yeah, the results were good. Yeah, so this is the work which was presented at ICLR. And now the future, what we are trying to study further is language agnostic spoken term search, because these models, they were not trained for a specific language, like ASR is for a specific language, but these models could be very general. I can train it on English, apply it on any Indian language, and can it efficiently do the task? So spoken term search, how effective it is. Then we are trying to test if it is able to learn the semantics that we actually want. For example, if I'm trying to search with respect to lyrics or with respect to melody, which means the melody is same, but lyrics are different, or melodies are different, but lyrics are same. So both these cases, am I able to control what the tokens represent? Do they represent explicitly the lyrics or explicitly the melody? Another work which we are doing is studying the linguistic properties of these tokens. Do these tokens correspond to the known linguistic forms? Because if we can establish that, then these methods will become very useful for automatic orthography generation for any language. Because then we know that, yes, these tokens actually are able to capture the linguistic properties. So therefore, they can be used as orthography. Okay, this was the, okay, now, if we have time, I can present another work maybe quickly on synchronous tokens. So this problem is query by example. So in the previous problem, I could say the same word myself, either slowly or quickly. The time synchronicity did not matter. But in many cases, we have, our query is synchronous with the actual target audio. For example, I have a snippet of the audio, the problem like Shazam handles, synchronous search. For example, I got a snippet from TV or from radio or from YouTube, and I want to find the original audio. So the query and the target audio, they are exactly synchronous, but the query may have noise or query may have some distortions, and query is a small snippet, whereas the original audio was a long audio file. So how do we efficiently search in this scenario? So this is the work we had in ISMIR last year and ICASSP this year. So the idea which we used was locality sensitive hashing. What is locality sensitive hashing? Basically, it does the tokenization, but it does it in a way that you have the entire space, you just learn some separators, and each separator, basically the separator boundaries will define a region, and this region can be called a one bucket. So if my query falls in some bucket, then I don't have to search in other buckets. I can just find out my search space is now very small within that bucket only. And then I can use methods like DDW or cosine similarity, which are more time-taking methods on continuous representations to do my search in this small space. Let's skip some mathematical details here. So we use the deep network to learn these hash tables. So we used contrastive learning approach, and the positive sample is, let's say, the clean audio. Negative sample can be created by adding some noise or distortions, etc., to that audio. And then we want to learn a mapping, or an embedding, which very faithfully puts both of them together, like our positive sample and the anchor and the positive sample are put together. Means my clean audio and my noisy version, they end up in the same bucket, or they end up with the same representation. That's the goal. So Shazam was our baseline, because Shazam exactly does this job, this task. And we tested with free music archives. So I'm skipping some details. For example, we used attention networks here to emulate the idea of Shazam, that we can focus on only the peak regions, etc. So the attention network will take care of that. Where do we want to focus? And then we tested with free music archives dataset, and these were the results. We are reporting here top 1 hit rate, means how many times we are able to find the right match at the topmost location. Means that the best match is the right match. So with our method, we got, let's say, at a very high SNR, means the signal is very clean, noise is very small. We got a high hit rate, 99%. But as the SNR is increasing, the noise level or the distortion levels are increasing, the performance is lower. With reverberation also, we see the same trend. But it is consistently better than Shazam, which is called out of print here. Now the question is this search really efficient? Yeah, we are learning some buckets and all, but which search is the most efficient? This is a kind of binary search in the buckets, but we know that binary search tree is more efficient only when we have a balanced binary search tree. So can we make the hash buckets balanced? It is possible that some buckets have lots and lots of entries, some buckets are totally empty. So it means with very few entries. Then using these buckets does not help much, because most of the time we will end up in the bucket which has lots of entries, and this is not computationally efficient. So our first work did not consider this fact, but our second work used this idea to make the buckets more balanced. How did we do that? We used an optimal transport plan. What is optimal transport? So this framework is mathematical framework. It has been used previously by people working in communications. When you want to transmit one signal to some number of users, and there are some intermediate stations which will relay your signal further. So you want to optimize the coverage of your signal with respect to those relay antennas, so that all relay antennas are working almost equally. You're not putting all the load on a single antenna. So that was the context in which this method was developed, but we modified it for our own purpose, that we want to get balanced hash tables. And it basically minimizes the, what is it called? The Wasserstein distance, or the earth movers distance. And the algorithm is also existing in the literature. It's called Synchronous algorithm, or SK algorithm. We simply used it with our network. And we found the results on the same free music archives dataset. We found that, yeah, I think this is the top K hit rate. Let me see. No, it's not. I forgot exactly. I think it is top K hit rate. Our top K hit rate is very much comparable to NAFP. NAFP is, I think, Google's method, neural audio fingerprinting method, and it's better than NAFP. And if we use the balanced hash tables versus LSH, so balanced hash table is, in performance, it is sometimes better, sometimes similar, but in terms of speed up, it is very fast, almost 2.4 times faster than those unbalanced buckets. So yeah, this was the work. Yeah, so that's it. So I think I presented about compressed tokens and about synchronized tokens. So thank you. Any questions I can answer?
Yeah, thank you very much, Vipul. Yeah, that's really impressive that you managed to maximize both accuracy and speed. The speed is also really important in these applications. Yeah. Okay, so if there's anybody in the audience who's questions, I know many of you work in very similar kinds of problems. So yeah, please ask.
Feel free to ask, even if it is a basic question, no problem.
So one thing that I was thinking, Vipul, is how do you decide the number of symbols in the orthography? Because towards the end you said that, okay, interpretation would be nice and so on. But even the performance, apart from the interpreter, would depend on that, right?
Yes.
So you're starting, I mean, it's really impressive that everything is unsupervised. And in fact, even your creation of the data is purely by augmentation, right?
Yeah.
So
we can use some label data to fine tune the things.
okay. So you mean that will help you also to identify how many symbols?
Yeah, for number of symbols, it's a hyperparameter, and we took it, let's say, close to 50 or 100 to make it similar to our languages, like our language 200 tokens. So we did some hyperparameter tuning, but means just tested on different values. So it's hyperparameter, and there are no set principle.
Okay.
You just see whichever performs the best.
And in the case of melody, will it work out to the number of distinct notes or something like that? Or
yeah, it depends, because sometimes our model may also capture some peculiar transitions. For example, in Indian music, we have transitions, etc., or some vibrations, vibrato, etc. So yeah, we want to use it for quantizing Indian music. So there, I'm not sure if every raga will have its own symbols, or this is the area of study we have not studied yet. We are working on it.
Right. Yeah, but at least now there's some kind of a systematic way to, with hyperparameters, to try out various, and maybe you can hit upon what is that, what's actually going to match some sort of notation, maybe.
Yeah. Yes.
And this nature of the data augmentation, because I like you said, how do you in your future work, let's say, switch from lyric-based similarity or melodic-based similarity to lyrics-based similarity? But that entirely depends on your the data augmentation, right? What you consider.
So we can control
to
it.
find a way, right. So just by that, you can essentially decide what kind of similarity gets captured.
Yeah.
Okay. Yeah, that's really interesting. So was this very complex to train?
The codes are available online. Somebody can try. It is a little bit that we have to make sure that it doesn't collapse. In the beginning, we were facing this problem that everything was collapsing to single cluster.
Oh, I see. Okay.
And, yeah.
So that's why that term in the loss is also important.
Yes.
Okay.
And the EM algorithm kind of approach where we cluster then freeze the
Correct. So you iterate and try to fix in the alternate stages. Okay. Yeah, excellent. Okay, anyone else? Anyone has a comment or a question or anything related to your work that you feel?
Hello, I'm Raju. So every audio is tokenized into some tokens, and those tokens are the fit size of tokens, or it can be learnable parameter. like in the discrete coding, those are the fixed number of tokens, or can we?
Yeah, right now we have kept it fixed. But yeah, somebody can try using agglomerative clustering or something to even learn them, but we have not tried that.
And also, you use the k-means algorithm. So how do you decide the k?
Yeah, we have decided it like a hyperparameter. We started with 50 or 100 different numbers, whichever worked best.
And also, can you please go through that site where you have done the edit distance-based fetching?
Please, pardon, I couldn't hear.
Can you please go to that slide where we have got the two tokens from different speech, and we are doing the edit distance-based matching. Can you please explain that?
In the theory.
The first
One?
yes.
Yeah.
Can you please go through?
Should I explain it?
Yes.
Okay. Let's say we start in the beginning with some random networks, means random initialization. Then this X will map to some set of vector embeddings and some set of tokens. These are repeated tokens, and then we compress them to make these tokens. And similarly, X dash will map to tau dash. Now, for CTC learning, we will map this X to tau dash and X dash to tau. So this cross mapping will help to bring them together. Or in other words, we are trying to minimize the edit distance between these two representations. Right.
Thank you very much. It was a nice.
I couldn't hear that, huh?
Thank you very much. It was a great.
Thank you.
Okay, so if there are no other questions, we'll thank Professor Arora for this talk. Yeah, thanks for taking the time, and yeah, let us know when where you post the recording as well, Vipul, right?
Sure. Thank you very much, Professor Rao, for giving me this chance, and to all the attendees. Thank you very much.
Yeah, I know. We look forward to this. Actually, many of these are also so important in products and applications. So I'm sure there's a lot you can do. Okay, fine. So yeah, people can leave if they want. Yeah.
Thank you. Thank you very much. Okay. Bye.